Okay, sir. Thank you so very much for your lecture series. We request you to deliver your next lecture in the series. Thank you.
Thank you very much. Yeah, this last day with this type of lectures, I will talk about reinforcement learning. And in the end, also a bit about these reduction methods I've talked quite much about earlier. So reinforcement learning is, I could say, I mean, it's a part of the new modern AI, where all people talk about machine learning. And you have already heard about that. And today I will focus about the more control-oriented part of learning, namely reinforcement learning. And in control, we actually have an old notion called adaptive control, which is quite much the same. Okay, there are maybe some small changes, especially the data structures that we are using nowadays with deep learning and so on, and that means that neural networks is very much the focus in all these learning areas. So we assume that we have a process and we have an agent that should in some way influence this process or plant, as we have also called it. And then the idea is that we get some feedback from the plant and try to formulate the criterion of how well the system performs in terms of what the goal is for our system. And then we try to learn something which we could consider actually as the value of this criterion in different regions of the state space. And based on that, we try to improve the performance. So we would like to improve the quality, and that is measured by criterion. Now the thing is that here we don't have a model, which, you know, we have talked a lot about that we have models in our system like automata differential equations or so. But here there is no model, is the assumption from the beginning. And then, of course, there are different strategies to handle this. And then there are different dialects of this reinforcement learning procedure. And one is that we assume that you go directly to the plant, the system you want to control, and based on that you pick up data and try to improve the performance of your system. On the other hand, the big problem, I would say, with all these type of learning procedures is that they require a lot of data. So we are talking about big data. And at the same time, I mean, that's the big thing here, that we have nowadays a big amount of data, and we want to use that fact. But when you go to real systems and try to online, say, for instance, I have some experience from manufacturing applications. You want to improve a manufacturing system, a production system. Say, for instance, in our case, we have looked for some years on the geometrical quality of plates when they are welding together. And then there are some clamps to fixate the different plates. Say that you are welding together two plates. They are fixated together by locators, and when they are fixed, then you come with a welding gun on a robot and you weld that. And the quality of that process of the result could then be measured, for instance, by scanning the system or the result. And based on that, we could see that, well, okay, it was not as good as we have expected. Maybe there is something we need to change by these locators and so on. Or another aspect is that, well, we have different types of plates here, different quality, and we want to sort them together so 1A and 1B could be a little bit different, and we try to match different A and Bs by scanning them and in that way match them in the best way together. In this case, I would say that we definitely don't have big data. We have rather small data. We have very few data, or we want to achieve a good result in a very short time. And this is totally opposite to what is expected in this learning procedure generally. So, I mean, reinforcement learning typically requires at least thousands or 10,000 data to get really good behavior. And we could say that if we don't know nothing from the beginning, I would say. But of course, it's also application dependent, but huge amount of data is typically a requirement. How that can be solved? Well, actually, there is a natural procedure here, and that is that we have from old days often quite good simulation models. So we go to the computer, and then in the computer system, we simulate the system. And then based on that, we try to obtain a first candidate of a good agent. So we can run this reinforcement learning procedure on the simulated process instead of the real one. And then when we think that we are reasonably close to good behavior, we can take the freedom to switch to, instead of taking data from the simulated model, we take data from the real process. And in that way, we could at least reasonably get a good behavior. On the other hand, then the question is, should we, when we switch to the real process, should we start, what should we then try to identify, or what kind of model would we like to get from this? And then one idea we have discussed quite much at our university and with some of my colleagues is that the process here, we have quite a good model of it. But if we just say, okay, we would like to identify the deviation, a model for the deviation between the real process and the simulated model, and that could be less demanding. And this type of thinking is something we have been working on for some time, but I have to unfortunately say that this learning of the, as we call it, the delta model, the delta is in this case the deviation between the real and the simulated plant, is something we haven't realized or we haven't fixed it yet. But I think this is, as a background discussion to this field, is quite an interesting thing, which we hope that we will get some closer to soon. There are also some other aspects on reinforcement learning, which I will come back to. But okay, to summarize the introduction here, we have feedback from the process, and we try to maximize a reward by making good decisions. And this agent, of course, learns from past experience. And then, of course, one challenge is if the process is changing, if it's not time invariant, then you must, so to say, forget old behavior with a reasonable speed. And this is a typical behavior and something that is very well understood in adaptive control, which is a technique that was developed especially here in Sweden. One of the pioneers was Professor Carl-Johan Åström and Björn Wittenmark, like 50 years ago. Okay, this is suitable for big data, but we have small data, and this is a challenge. Now, there are two topics related to reinforcement learning that we need to understand better. And one is the optimization procedure, and that is based on what we call dynamic programming. So you could say that reinforcement learning is a slight modification or generalization or modification of dynamic programming, Bellman's optimization principle. So I will illustrate that problem a little bit, but more in the beginning here, also introduce the notion of Markov decision processes, MDP. And that is a big field within stochastic systems, probability theory. And it is actually related to the kind of automata we have talked about earlier in this course. And it is then related to the assumption that there are different probabilities to go to different new states. And based on this, there are conditional probabilities and there are state probabilities and so on. And to fully understand this, we should even go back to Markov processes and Markov chains. Now, that would take quite a long time before we are then back to reinforcement learning. So what I will do now is that I will only go for Markov decision processes. And if we have time in the evening pass, I will go back to Markov processes in general and also illustrate the classical problem there called queuing system and queuing theory, which is also an interesting aspect. So with this background, I switch back to here Markov decision processes now. And the background for us is that, yes, we have an automaton and we could make a decision to take an action A or B. And here we can say within Markov decision processes, we only talk about actions, not events anymore. The notion is actions. And you could say that it's maybe mainly because it's a kind of control procedure we are talking about, or decision procedure. Now, what is the difference between an ordinary automaton and an MDP? We say often Markov decision process, MDP. That is the general notion. Well, here we have action A. And if we take that action, we know that from the initial state here, we go to this state. No question. But if we take a B, then there is probability 0.6 that we go to this state, and there is a probability 0.4 that we go to the lowest state here. So these are what we call transition probabilities, and they are actually also what we call conditional probabilities. If we are in this specific state, what is then the probability that we go to this state? But also coupled to the fact that we take the action B. So there are two conditions, action B and that we are in this state. And then you see that these two probabilities, they sum up to 1. And that is a probability distribution should always sum up to 1. So this is the basic thing around this. And I will show you some examples later on how we can use this when we also introduce learning. Here to illustrate this MDP procedure, there is a classical example on repair or replace a machine or a tool, a printer or something. which is quite well known in the literature. I have seen it in at least 2 books, and I also found it in papers. Okay, so the idea here is that from the beginning we assume that we have a machine, for simplicity I call it from now machine, that is in the state Q1, which means that it is as good as a new machine from the beginning. Then we have the other states here, and that Q2 follow here with going from Q1 to Q2 with probability 7 divided by 8. And that is that it's operable, but with minor deterioration, minor loss. And then the third state, then we have major deterioration, major loss of the products produced by this machine, because it started to become quite bad. And then we have the last state where it doesn't work at all, it's inoperable. And in this state, we need to replace the machine. So when we have come to this state, we need to buy a new machine. Is the assumption. And then we go back to state Q1. So in this case, state Q4, there is only one output transition with probability 1, and that is buy a new one. So far, I haven't given any costs of these transitions. That comes later. But now it's interesting also that when you are in this first state with a good machine, there is an assumption that even a small probability that it's next, even in next state, becomes inoperable, doesn't work. And I mean, that's tries to say that, well, okay, even, I mean, some electronics, if they, either it works for a long time or something happens very early. So there is a small chance. Okay, only, I mean, this chance is quite big if we come look at this. And you could say that the numbers here, they are more or less also chosen. I've taken them from the sources I've looked at, but I mean, they are formulated just to make it reasonably easy to make calculations here in the end. So from the good state, of course, the most probable situation is that you go to the state 2, where it's operable with minor deterioration. Actually, there could also have been a self loop here, that you stay here in as a good as new, which maybe surprises me a bit when I look at it now. But in state Q2, there is 75% that also in next state, after next iteration, next update, you're still in this state where it's operable with minor deterioration. But there is a small chance that it's even already in the next update that we go to a major deterioration. And these are the only, okay, even in this state, it's a small chance also that it doesn't work anymore. So far, we haven't had any decisions involved here. And that, because that comes in the third state here. And then there are 2 decisions, or actually 3 decisions. Because now the machine starts to become a bit bad, and you know, if you own a car, it's always a discussion, what should you do? Should you do like me? I'm buying not totally new, but reasonably new car. And then I don't like car business, so I typically had the car many years. And the last one I had to, yeah, it was useless in the end. So that is just to wait to see to be able to use it as long as possible, and that means that you stay in this state, continue to use existing machine. Another way is to repair the machine, and okay, a car you always need to repair when it gets old, but okay, for the machine you could have two choices there: either repair or continue to use it as it is right now. And then if you take the first decision, A1, there is 50% that it will continue to work in with this major loss, and there is 50% that it is inoperable and you need to replace it. Also in this state 3, there is an option that you could buy a new one already here, depending on the costs here. I mean, to stay here with major loss, that costs. How much does that cost compared to buy a new one? Yeah, I mean, those could be the things could be discussed. So here we have 3 different actions, and we have 4 different states, and we have then now a set of actions. And if you look at all these probabilities here, they are summed up in what we call a conditional probability matrix. So let's look at the first row here. That is related to the first state, Q1, and then it's probability 0 that you go back to Q1. So even in the next update, you either go to Q2 with probability 7 divided by 8, to Q3, 1 divided by 16, Q4, 1 divided by 16. And then for the second state, you have 3/4 that you are in state 2 and less to go to state 3 and 4. When you are in state 3, there are different probabilities depending on which action you take. So far I just put general notions is P31, P32, etc. And in the fourth state, there is only one alternative, buy a new one, and then it's probability 1 that you go back to state 1 from state 4. So this is the background to this example, and now the question is, how should we optimize this system? Meaning that which action should we take in state 3? What is the best action? And of course, that is very much depending on which cost we have. And then you could say that if you're talking about cost or reward, in reinforcement learning, the tradition is to talk about reward. If you would like to maximize something, so the maximize the profit, for instance, or the opposite, minimize the cost. And here we can say that if I go to the cost here, there are some costs related to the different actions here, and they come later, and then the question is, how should we handle this? And then I think I take a little bit on this to understand this fully. I introduced here a cost function, one for A1 and one for A2 and one for A3, and then they are related to the product of the probability, the state probability. So if you are in state 3 and you have a cost in state 3, I could just show you here. Okay. I think that the cost to stay in state 3 is 3, and in state 4 it's 6. Let's see. Yeah. So the general assumption here is that to buy a new one, that costs 6 units. And you have minor loss when you are in the state 2, where you have and that costs 1 unit. Then you have the different costs in state 3, and here you see that it's a cost 3 to stay where you are, and cost 4 to repair, and cost 6 to buy a new one. And those were the 3 different actions. So here, depending on the action you take, you have different costs. And then for these states, we simply need to determine which is now the probability that you are in state 0, 1, 2, 3, or 4. And that decides, of course, which will be the total cost. Because if it's 50% that you are in state 3, then you should multiply this cost 3 with 0.5, and say it's 25% that you are in state 4, then you should multiply that by, or divide that by 4. So once again, the cost for the different actions are the state probability multiplied by the cost in the different states. So now the challenge is here, actually, in the calculations, is to determine the state probabilities. And then it can be shown with some statistics or some probability theory that the state probability is given by this equation, this conditional probability matrix, which we have formulated here with a lot of variables on the third line. I will come back to those variables, but given that conditional probability, the state probability is the total probability to be in a specific state, is then given by this equation. P is equal P multiplied by capital P. And P is then the vector, including the elements P1, P2, P3, and P4, the state probabilities. Observe once again that state probabilities and conditional probability are not the same. The conditional probability implies that you are in a given state, and it says how big is the probability that you go to another state or that you stay where you are. When you talk about the state probability, you just look at the whole system and ask, okay, what is now the probability that the system is in state 1, 2, 3, or 4? And that is answered without any conditions. Is answered by this p-bar vector. So then the A1 solution was that you should stay where we are, and then it was probability 0.5 that we are going back to the, so to say, bad state, and probability 0.5 that we go to the damaged state. So those were the only ones where we had not probability 1, but so here is the same probability, half of it, to stay where you are or go to the state where the machine doesn't work anymore. For action 2, it was to repair, and then the conditional probability is 1, that we go from state 3 to state 2, and the rest of these parameters are 0. And in with the third action, then it's the question if we buy a new one, even when we are the machine hasn't broken, it's not broken, but it works badly. Then it's probability 1 that you go from the third to the first state, and the rest of them are 0. So if we then take the second decision here, it means that we put P32 equal 1. And this is the repair strategy. And then you have now a specific probability matrix. And then to calculate, to get the P bar, I will not discuss all the details in the calculation, but just showing the principles here. Here we have the different variables, and which we are, in principle, trying to solve a linear equation. Here we have the probability matrix P for the specific choice of action, it's important to say. So then when you multiply this matrix with this row vector, that generates actually these elements. So just we can see that the first column here multiplied with this vector generates the element P4, and that should instead also be matched by P1 here, because this element should be matched by P1, yes. So that means that we have already got one solution here. P1 is equal to P4, and we define that by just calling that P. And then you see that the other ones, for instance, P3 and P4, they are equal. Since P4 is equal to P, then it means that also P3 is equal to P. And then we have another important aspect, and that is that the sum of all the state probabilities must be equal to 1. Once again, when you sum up all probabilities, that must be equal to 1. And that means that you have actually a condition even on P2, and that is 1 minus the other probabilities, and they were all P, so those sum up together get 1 minus 3P. If you then introduce that in one of the equations, say the one for P2, then it's just straightforward calculations, algebraic manipulations, and you get P2. 15 divided by 21, and based on that you can also determine the rest of them. And you see here that the rest of the terms here, they they should be equal. So it's 2 divided by 21 in the rest of this. And we see that if you sum up all these elements, you get 21 by 21, then that means 1. So by this, we have now calculated the state probabilities, and then we are ready to introduce the different, we have solved this now for action 2, and then we can, in the same way, solve it also for action A1 and A3. And then I've already discussed the costs here. So now we have the state probabilities for the different actions and for the different costs. And then it's just to take this P vectors, multiply by the cost vector for the different actions, and you get actually 3 different numbers. And then it says that to stay where you are, doing nothing, cost 1.9. To decide to repair cost 1.67, and to buy a new one cost 1.73. So the minimization of this criterion for the different actions is actually to take decision A2. And policy A2 gives the lowest cost, including minor loss in Q2, repair in state Q3, and replacement in state Q4. No surprise, of course, with all these sustainability aspects we have today. To repair a machine should always be the best solution, because then it means that it can live a longer life. Okay, in the end, it does not work either. But this illustrates at least the way in which we can act with these Markov decision processes. So generally, with a Markov decision process, we have we have transition probabilities for the different actions. We sum that up in a P matrix, and then for the different actions, we solve the state probability, and then calculate a cost function, the value of a cost function for the different actions. That is the general procedure. Now, this has been solved for a stationary case. Then within reinforcement learning, it's more of a dynamic system we are looking at. So I will come back to that. So once again, about reinforcement learning then, it's an optimization method where actions are sent to the plant and resulting rewards are evaluated such that optimal actions are selected after initial learning phase. And this initial learning phase could be then based on, say, a simulation model. And reinforcement learning is extremely popular at the moment. And just to mention about AlphaGo is a popular program where its success is based on reinforcement learning. So now we go on with the optimization part of this. And okay, we could say that I have shown an optimization procedure, but that is based on this infinite time horizon, actually the stationary behavior. And that is, if you go for reinforcement learning and so on, it's quite complex mathematics behind this. If you don't go for this very I would say non-efficient method to solve for when you have a huge number of states, etc. But what is used in dynamic programming, in reinforcement learning, is actually to use the procedure of dynamic programming. So that's what I want to show right now. And now I take actually a deterministic picture here. And it's interesting that the first slide I showed you here, an ordinary automaton without any transition probabilities is sometimes within this area of MDP and reinforcement learning. So it's sometimes called a deterministic MDP problem, while this is a probabilistic MDP problem. In my view, I would say that, it's first an MDP if you introduce these transition probabilities. On the other hand, we can say that MDP is extremely well established as a tool to solve this type of optimization problems. So in the operation research area, it's quite common that they call even an automaton and deterministic MDP. So here we now assume that we only have, from the beginning here, we only have an automaton. And then we introduce rewards for the different transitions here. So for instance, here from state 1, taking the action B, then I assume I get a reward 2 to get to state 2. And from state 1 to go to state 3, I get a reward 5. And that's what's repeated up here. So you see that this automaton has been complemented now with rewards, local rewards, immediate rewards, they are also called. And then you could say that, well, we should just simply find the way to this state 6, which gives us the best reward. And that means the highest sum of the reward of the immediate rewards. So the optimization here is generally based on all types of actions. And then you could say that this C, B, D, E, F, they are actions now. And why I write A, K, etc. depends on the fact that, okay, now I assume that I am in state xk, and xk, it's a time instance k, but it could be any of the states here. Assume that I'm in state 3 at time k, and then I ask myself, what is the best solution when I am in this state to reach the final state? And that is to maximize the rewards for the coming states from 3. Actually, this was a bad choice here. We go back to state 1. Okay, here I have 2 choices, either to take B or C. And when I'm in state 2, I can take D or C, but after that, it's only F. So the one idea with the dynamic programming is that you could start in the final states and go backward and see that, okay, if I am in state 5, what is then the best choice? Of course, it's only to take an F. Also, if the reward then is 3 because you get 3 there. You could also check here if you take an F and come from state 4, then you get more rewards in that state. You only get 7. So obviously, the 2 alternatives here is that, okay, it seems to be much better to go from state 4. And then if we look at the 2 alternatives here, we see that, well, okay, if I go backward here, the optimal choice in state 2 is to take C. And actually there I had an alternative because I could also have taken a D. And if you look at C, you find that, okay, here I get 3 plus 7, it means 10. While if I take this route, I only get, 3 plus 7. 3 plus 7, I get 10, and 4 plus 3, I get 7. So this is the best choice from state 2, and then I get a reward 10. Now we had checked from state 2, 4, and 5, and now we look at state 3. And then we see that from state 3, this way I only get 5, and you could say that it's actually not necessary to go the whole road, because it's enough that I go to the next state, and then I find that gave me 3 for the rest. So 2 plus 3 is 5. But if I take this road instead up here with an E, I get 2 plus what I have in state 4, namely 7, and that means that I have a reward 9 in this state. Okay, So now, based on what I have here, I can go one step back again, and then I see that if I take here I have two alternatives. I can either go for B or C. If I take a B, then I have 2 plus 10, 12. And with the C, I get 5 plus 9. That means 14. So obviously, it was better to take the C action. And now I have gone through all the states here, and I have in every state the best choice. On the other hand, we could say that, okay, if you have a given initial state and a given final state, of course, the only thing you are looking for is the best route from this state. But you get more or less for free these other states also. It's a straightforward iteration to go through the system. And the Bellman's principle is that, okay, if I am looking at this state and I know that from the next state, I know the best choice. And then it's obvious that I don't need to look at the rest. It's enough to look at what is the rewards in the next states and just add the current state to the next state. And that is very, very simple principle, but it's called Bellman's optimization principles in dynamic programming. Bellman was an extremely innovative person within operation research and etc. And it looks so simple here, but actually Bellman's principles has, as in some other formulations, a more involved interpretation. So the optimal action here is to take C, E, and F in the different states. So when you are in state 1, you should take a C. When you're in state 2, okay, here the actions is actually mentioned for all the states here. But if we are in state 1, E, and then E and F, and then you have get the optimal solution. So this is dynamic programming, and the basic idea around this is something we will also use in reinforcement learning. So now I will go through a text I have here, and then I will extend that a little bit in a research paper I presented 2 years. Yeah. 2 years ago. At least I submitted it 2 years ago. And that is an extension of reinforcement learning when I combine that with temporal logic. But first we go through the basic reinforcement learning. And then based on dynamic programming and a transition function, okay, we can say, yes, reinforcement learning is based on dynamic programming, and you assume that you have a transition function for every state. The thing is that now we assume that we know this transition function, and even we have a reward function. So the next state and the reward in the next state is given by these functions. The thing is that these functions are not known in the final method. Then the assumption is that we can replace this transition function by observations from the real plant or from the simulation. But that is coming later on. So now we assume that we know these transition and reward functions. So based on that knowledge, we are searching for an optimal action sequence. And that can be described as an action sequence from A0, A1, A2, etc. until infinity in general, but it could also be that we have a limited horizon. but from the beginning here we formulated to infinity. And a control policy is a function based on which state you are in. And that should lead to an optimal infinite horizon discounted value function. And discounted means that I take the sum of the local or the immediate rewards based on the reward function. But I multiply with gamma to the power of k. And that means that when k get large, if gamma is a little bit less than 1, that will be a small number. Gamma k will then be small, while of course gamma to the power of 0 is 1. So say for simplicity that gamma is 0.9, then the first is multiplied by 1, the second by 0.9, the third, a third time instance by 0.81, etc. So you get less and less contribution from future rewards. And this discounting factor is simply introduced to decide how far ahead these rewards should influence the control policy at time k equals 0. But it also means that since gamma is less than 1, it means that you get a finite criterion, which is another theoretical important aspect here. Remember that this is formulated now for an arbitrary initial state, x0. Now, Bellman's principles is the following, that you take the first element in the sum, which is rho of x0, a0, plus the rest of this sum. But in that case, when you start with k equal 1, it means that you can take away 1 gamma out of this sum, and you can update this as follows. So you have gamma now for a maximization of, and now I replace xk with xk plus 1 and ak plus 1, because I want to sum still from k equals 0 to infinity. And it means that also here I have maximization of ak plus 1 from k equal 0 to infinity. The interesting thing is that what is said here is more or less the same as we have up here. It's the j star at time instant x1 instead. So we have formulated the sum using actually Bellman's principles here, that we maximize now with respect to the first action a0, adding the immediate reward from x0 with a0, the initial state with the action a0. There could be a number of different possible actions here, as we had with this repair, buy new, or stay where you are in the MDP example. Then you have gamma of j star x1. But what is x1? It's delta of x0, a0. Then we're using the transition function. So this expression can be applied actually not only on state x0, it can be applied on any state, j star of x. And that means that with respect to all what we have earlier called active events in state x, which possible actions are possible to take in state x, they are defined by sigma of x. On those possible actions A, we should maximize rho of x comma a instead of x0, because now we have an arbitrary x, not x0. plus gamma j star of delta of x comma a. And this is what is called the famous equation, Bellman equation, which is the core of dynamic programming. Now we can apply this to this example, which is, I mean, it's a little bit different to the one we looked at before, and also there are no probabilities here. So let's see how this works. We take this equation, j star of 1 is the maximization of the possible actions in this state 1. And obviously the alternatives are action B or C. And then we express the different possibilities here. And they are then rho of 1, comma B and 1, comma C. And then we should also introduce, we should maximize with respect to these different possible rho, and also plus gamma j star for the next state. And the next state, what is that? Well, the next state is 2 in this case. So here we have gamma j star next state, which is 2. Then we see that rho of with action B, the reward was 1. With action C, the reward is 2 instead. So we should maximize with respect to 1, comma 2, and of course then the maximum is 2 of those elements. So then we get 2 plus gamma of j star of 2. And then we continue, because now we have a relation between j star of 1 and j star of 2. And j star of 2, then we can apply again the Bellman equation. So then we should maximize with respect to the 2 choices in state 2, which was D or E, with reward 4 or 3, plus gamma multiplied by the optimal value in the next state. And you see here that I don't know what these j stars should be. I just put them as, if you call it variable or values of, or expressions for this j star function. So they are something we are looking for. But then we could get j star of 2 equal 4 plus gamma of j star of 1. And here it's interesting that we get once again a fixed point. And a fixed point is something that now we introduce what is j star of 2. And there we have expression for that. It's 4 plus gamma j star of 1. And suddenly we have now got an equation for j star 1. And the solution to that is 2 plus 4 gamma divided by 1 minus gamma square. Just to solve this equation with j star 1 as the unknown. And given that, you can also easily formulate what j star 2 is, just 4 plus gamma j star 1. And the fact that we get this, this fixed point or iteration is interesting in itself, but that's actually a general result for dynamic programming. Once again, note that we don't have any probabilities here. Now we come to this very famous and special Q function in reinforcement learning. So you could say that there were some people well, how long time ago was it? I think it was around 1960 or so. So 50, 60 years ago. There were some results where they realized that, okay, dynamic programming could actually be, or Bellman's equation could be reformulated in an interesting way. And then we say that the argument in the criterion in Bellman's equation, this one, let's call this Q. And I mean, in all papers, this function is called the Q, and it is the Q function. That is the most common or special word in reinforcement learning, is the Q function. And here you see then that if you do that, you get J star of X is equal maximum of on maximization on the different actions for this Q function. So then it's interesting that while J star only depends on the state X, the Q function also depends on the action A and the state X, and that is actually the secret or the good thing with this formulation. So if we introduce Q function equal rho plus gamma J star, then we have a state action pair, which is also an important notion here. We have a state action pair, and for that we can then search for the best action, that the one that maximizes this Q function. So where J star of X is equal maximum with respect to all the possible A, and then we maximize the Q function on this. So now Bellman's equation is expressed in terms of the Q function instead of the original function. And then it's interesting to see that also this Q function can be formulated. We can replace this J star here. Actually, J star in this Q function is the maximum of the Q function. So it's just that we introduced this expression here. But then remember that we should take J star of delta of X comma A or X prime. So in the Q function here, instead of writing Q of X here, I need to rewrite Q of X prime, or the next state, but that is also delta of X comma A. And then I now need to introduce another decision variable or action variable, and I call that B. And that is then the best action in the next state, X prime or delta of X comma A. So this is really a famous equation. Q of X comma A is rho of X comma A plus gamma of mix of maximum with respect to the possible actions in the next state of the Q function in the next state. Okay, how can we use this now? Well, for all possible actions, we are looking for the optimal one, which determines the optimal control action. And here comes the great thing, that if we now happen to have the solution to this equation, which we don't have yet. I mean, we just have formulated an equation. But assume that we know this Q function for the different states and actions. Then for every state X, we could simply take this Q function and look at the argument which A gives us the best value of this Q function. And that we can call A star. the argument that gives us the maximization of this Q function is is the A, which gives the best value, and we call that A star. So mu x, the optimal control action, is this A star, which maximizes the Q function. So based on our former example here, we can actually formulate not only J star, we can also get the Q function. Look at this. Q of x is rho plus gamma J star of delta. Then we take this for x is equal 1 and the action B in this case. And that is then the rho value for x equal 1 and action B, that rho value was 1. Let's see. Yeah, B has reward 1 and C has reward 2. So here we get for action B, we get 1 plus gamma J star 2. And for action C, we get 2 plus gamma J star 2. And for in state 2, we had 2 different actions, D or E, and they had reward 4 and 3. And then it's 4 plus gamma J star 1, etc. Now we have, in our case, actually values. We have determined the J star values. And based on that, we can put in these numbers and conclude that the ones that give us the best Q function in state 1 was actually action C. How can we see this? Well, because we see that the Q function has J star 2, in this case at least, as the next argument. So it's just to look in this case at the immediate reward, and then we see that the C gives us the best. And in state 2, it's D that gives us the best reward. That you have this simple solution is of course not always the case, but in this case we got this. So with this very extensive procedure, we have actually obtained the optimal policy. Choose C in state 1 and D in state 2. We can just look back here and see that, yes, it looks quite reasonable that since you have to make a choice between one action which gives you only 1, but you have another one which gives you 2, it sounds reasonable that you take 2. And here you can choose between D that gives you 4 and E that gives you 3. And then, of course, 4 is better than 3. But I remind you that in this case, we had a bit more tough choices or more options, so to say. So then it was not so easy. So now we can say that, well, we have solved the optimization problem, but that depends 100% on that we have a model. And that means that we are not yet within reinforcement learning, but we are very close to reinforcement learning, actually, because what we have shown now is a model-based Q function solution. And what we will do now is quite a simple reformulation of this and get what is called the model-free Q function. So I think we take this and after that we take a break. So replace that. I will show you one more slide before.
Okay.
So the model-free Q function iteration is simply achieved by replacing the delta function, which is the model, with a measurement from the real plant, from the real process of the next state. And that means that we need to choose an action A and look at which next state do we get, and also which immediate reward do we get at the next state. So this prime means next state and next reward. So what we do is that we send an action to the plant and wait for the next state and the next transition reward. And then we should update this Q function, which we have here. The problem is that we don't know the Q function, but what we assume then is that we have an estimate of the Q function. So we can say first that generally we replace now the raw function with next reward and the delta function with next state. But the problem is, once again, that we don't know the Q function. On the other hand, as in many other applications, we could start with some guess, an estimate, and then simply iterate this equation. And then is the question, how do we iterate this equation? The next value is then equal to the next estimate is equal to the current estimate. It should be an x here. So x hat k plus 1 is q hat k plus 1 is equal to q hat k for x of a, with sort of say a factor which is a little bit less than 1, at least we could say. And this is what is called a learning factor. We could say that if we have a good estimate of q hat, then alpha should be quite low. Then we should trust quite much on the former estimate or the current estimate. But in the beginning, we don't know anything at all. So then we have an extremely poor estimate. So then we should have alpha close to 1. And then we must trust very much on the immediate reward we get from the next sample. We send out an action, see which reward we get. But we also look at the next value of the Q function in the next state and maximize that. And that is simply based on this element of the Q function. So we can say that what we do is that we take this equation, we multiply this expression with a learning factor, which from the beginning is quite large. It's quite close to 1. But when time is going and we get better estimate, we trust more on what we have really achieved, of what we have already achieved, and that means that we trust more on the current estimate when we get an update of the estimate. Okay, in most cases, the action is selected to maximize the Q hat function, as we have here. But then the problem is that we must also be sure that we explore most of the state space. So to explore the whole state space, there is a strategy called epsilon greedy. And it means that it's also necessary to take actions which do not maximize Q hat. So an alternative arbitrary action is then taken. Instead of maximizing this, we just take an arbitrary action within the set of possible actions. And that is done with equal, uniform, but reduced probability. And this procedure is then done for all actions in sigma of x and for all states. And the optimal so-called greedy solution is then taken with probability 1 minus pk, which goes to 1 when k is going to infinity. So that means that the greedy solution to take any action, that is what you do more in the beginning, and after some time you more trust on your Q function, and you maximize more, you take more of the maximization strategy. So this function, Q function, is not that difficult to implement. And I think also that I can show you this evening a short implementation of that, which I've done myself in MATLAB. This was just an example similar to the one I've shown you before. So to repeat here, or to summarize, the reinforcement learning, the basic one, which is called then Q learning, is based on updating and learning this function Q. And then there are of course a lot of different strategies to solve these tuning factors, like the learning factor. This epsilon greedy procedure is not the only one that could be used. So you could say that there is a general conflict between exploring the whole state space to be sure that you don't miss some important areas, and to focus on the optimal solution. And in the beginning you try to explore more of the whole area, state space, and after some time you trust more in the obtained Q function, and you go more for optimality. But this procedure, as you could imagine, based on this, if you have a large state space, requires a lot of iterations before you get a good Q function. But reinforcement learning altogether is to get a good Q function, because if you have a relevant Q function, it's also very easy to get the best possible control action, optimal control action. So this is an optimization procedure based on the fact that you learn from the process, and this is reinforcement learning. So let's stop there and take say 5 minutes break, and you can ask questions. Let's see if we have one here. How do we decide the value of gamma? Oh yeah, that's a good question. Yeah, the gamma value is typically quite close to 1. It could be, I mean, depending on how large time horizon you would like to extend to it, 0.9 to 0.99, I would say, are standard choices for this parameter. So then I will take a short break also, and we can continue. So. Are there any more questions?
Yes, Professor. I don't find any questions still. Participants, if you have any questions, please feel free in asking. Unmute yourself.
Is there any one of you who have tried this before? Or?
Hello. Hello. Professor, you were asking something. I didn't get it. Can you come again, please? Hello.
Okay. Yeah, then I think we can go on.
No, you were asking something. I didn't get your. I couldn't get what you were saying. Are you getting my voice?
Yeah, we hear you, but
Okay.
yeah.
All right. So we can begin with the next part, Professor.
Yes.
Thank you.
Okay, so then we now I will make some extension of this, and this is a presentation I gave in November 1.5 years ago on a workshop for discrete event systems. So that indicates that we try to also push in this direction also in the discrete event area. And the reaction I got on that paper was that, well, it's more or less nothing new in what you present here. We have all seen it all before. But at the same time, I see here that there is quite a big interest on also including temporal logic into this reinforcement learning area. So in some sense, this is a repetition, but also a generalization of what I showed you before, and that gives you definitely some additional features. So now we present the Markov decision process as a tuple. And yeah, this set of states is always a pity. What should we call it? In our area, we have quite much called it the state of the set of states capital X or the set of states capital Q. But in the reinforcement learning area and in operation research in general, it's the set of states is mostly called this set S as in states, and then A as in finite set of actions, while I used to often use the word sigma there. So that's a lot of frustrations for myself, actually, that my own field, discrete event systems, use different notations here. And but it's always this situation where you are working in a new area. The notations have not been completely established. And then we have the probability function, this transition probability, and that is actually this conditional probability that I was mentioned on before. So for a given state, what is the probability that you at next state with an action A go to S prime? And when you sum up all these states for a given action, but for all possible next states, then the sum should be equal 1. It could actually be reduced to the set of possible actions which states they are involved in. But okay, this is fine. And then you have an initial state, and you also have here atomic propositions and a state labeling function and a reward function. The reason why I introduced these atomic propositions and the state labeling functions is simply because I want to introduce temporal logic, and temporal logic is mainly based on state labels. So that's, you could say that these atomic proposition and state labels are not so common in otherwise in MDP. So now I give you 2 examples of MDPs, which I have run a bit myself here, as trying to find something of some interest. So here we have 2 states with labels, state 1 and 3. And state 1 is also the initial state, so you can go to state 2. And there I have at least one situation where I have different state or probabilities. No, sorry. This is the reward. You have different rewards here if you take A or B. So if you take an A, you get 0.5. If you take a B, you get 1. So in this case, actually, you don't get. This is not a probabilistic one. It only includes deterministic situation. But you have, at least in this case, 2 alternatives where it's of interest to introduce different rewards. In the next one here, the idea is that this is actually a bad state. So we could call R a forbidden state even. So we definitely don't want to reach into this state. And then you see I've introduced here an action with probability 0.1 to reach this when I get into state 1, and 0.9 to avoid the bad state. So here we could already see that, well, is it even okay to move to this state 1? In fact, not, because there is a small probability that we will reach this forbidden state. So the MDP or the reinforcement learning procedure, the Q function, need to learn that, okay, if you go into this state, it's really bad, because then it's risk that you get into this forbidden state. But remember, it's not 100% true. So it's interesting to see how fast this learning procedure goes then. So then you can go around within this loop, but you can also go down here, and it's a possibility that you can walk around here also, which is maybe not so good, because we would like to get back to this P state. But here we also have an interesting situation, because you can also take the right direction here, and from the beginning, no problem, no problem, no problem. But here, after 4 or 5 steps, you get into a forbidden state again. So then it's interesting to see how fast does the learning mechanism realize that, okay, well, to take a C here in state 3 is really bad. You must take a D. So especially the second example here has some aspects of good and bad states, and that can be interesting to see how this can be learned. Okay, then we also need to introduce the synchronous composition between different models. And now we have also to take care of the transition probabilities when we take an action that is shared between the two MDPs. And in that case, you have to multiply the probabilities for the two individual models. While if it's a non-shared, if it's a local event, then you just take it as it is. Here I've also introduced something quite useful, and I have never seen this in any other place, but it gives some extra burden, but still important, I would say. And that is that different atomic prepositions, you have different expectations on if they should be, if you should require them in both models or not. And then I've said before that marked states, they should be marked in both of the models, in this case, both the MDPs, to be marked also in the synchronized system. While if you have a forbidden state, it's quite natural to say, okay, if you have a forbidden state in the first system, it doesn't matter where the second system is. If the total system is in the forbidden state in the first model, it's absolutely a forbidden state also in the total system, in the synchronized system. So there is a stronger demand on that you immediately get forbidden if you have only a forbidden state in one of the systems. So for a forbidden state, I use this or condition. That so AP1 or includes the forbidden states, and AP2 or includes also the forbidden states. While marked states are included in this part where we take the intersection. It must be both part of you must have a marked state in both the second and the first and the second part of the synchronization. Then there is a state labeling and a reward function. The reward function then includes, of course, now both the states. And if it's a shared event, you take the sum of the rewards in the individual systems. To illustrate this stuff on the forbidden and marked, I have two deterministic MDPs, if you like, ordinary automata, in fact. And in the second one, you have two choices with the event B. You can get either to a forbidden or a marked state. If you now take the synchronous composition of these two, you get these 6 states. You have the initial state, and then you have combinations of the first state with the 2 second, that gives you 2 state combinations, and this one combined with all the 3 here, it gives you 3 different states. Altogether here, we see that if the second state is in state 1, it's a forbidden state, and it's forbidden independently of where the first system is. The first system is actually does not have a marked a marking state label for forbidden. It only has a marked label. But if the second one is in a forbidden, the whole system, the synchronous system, is forbidden. While the marked states, you have, it's only in state 1, 2, where both M1 and M2 are in a marked state, where the total system is marked. This is just a repetition of linear temporal logic, where we can just point out, say, for instance, that always P means that you have P in all states in a sequence, and eventually P means that after some time you must at least get a P, and this infinitely often square diamond P and not P, okay, but P must come sooner or later, and that is repeated. Now there is a technique which I haven't talked about before, but for LTL, a common strategy, a typical strategy is actually not to use the mu calculus as I described before. It's to translate the temporal logic property or formula into something that is an automaton with an equivalent behavior. And in this case, we can say we have an original system here, an MDP with here one state Q and one state P with state label P. And then we can just look at this temporal logic expression and the corresponding so-called Biki Automata. Here it's interesting that, okay, obviously it should never have Q, because it should be always not Q. So that means that as soon as you get a Q, you have not satisfied this part, always not Q. And that means that, and okay, here in the Biki Automata, it's interesting that now it is actually the state labels that are introduced as transition labels. And this is a type of complication which can be a bit confusing. But think about if you are in state 0 or 1 here, and if you get suddenly a state where Q is true, and that is exactly the meaning of this, and it means that also here the cross product or the combination of M and B is a little bit involved, because it has to look at the transition in M and look at which is the state label you are arriving, and that generates a transition and the corresponding transition in then the B function. Okay, once again, a Q means that you get into this forbidden state. And if you combine these two models, you see here that when you are in state, when you reach into state 1 in M, you also reach into state 2 in the Biki automaton, and 1, 2 is then a forbidden state in the combined system. While then the question is, what is up here? Well, it's more related to this eventually P. So if you don't have P, if you don't go into a state with a P and also not Q, then you can stay where you are. But if you have a transition to a state with P and not Q, I mean, not Q must always be satisfied, because this safety specification, always not P, always not Q, sorry. But eventually P, when then suddenly P becomes true, you move to this state 1, because then P has happened one time. And then it doesn't matter what P is for the future. The only thing we need to take care of is that, okay, Q is not allowed to be true, because then you move down to this state, while as long as it's not true, we have not Q, then you can stay in this, so to say, goal state. Now look at this Biki automaton together with the original model, and then we see that, okay, when action B happened in the original model, then the synchronized system with this specific or combination, I would say of M and B with the event action B, then you get into state 2 of M and into state 1 of the Biki automaton, 2,1, and since then 1 is marked as a goal state in the Biki, also the total state here is marked. And after that, you have a C, and then C will be repeated. And here you will go on forever with the C in state 3, while you are still in the marked state in the Biki automaton. And if you have then an infinite loop where you repeatedly get into a marked state, then you satisfy this expression. And here you definitely satisfy because you are always in a marked state. But it's a wicked condition. It's enough that you have this property always, eventually, this marked state, going to this marked state, then it's fine. So this is a specification of the combined behavior, and that means that we must, of course, avoid this one state, because then we get into a bad situation, while we can accept this B and C actions. So this was temporal logic and related automata to this. Now the question is, how can we use that together with reinforcement learning? Now I repeat this dynamic programming part, and just to make a switch here to get some flavor of what is coming, I will also introduce the Q-learning. And now I will even explain how the Q-learning can be derived in a probabilistic setting, which was quite interesting, at least for me, because it is actually a very, very simple procedure that is behind the theory here, which I was not aware of. And I would say that in the literature, this is quite often not described in a good way to make it understandable. I hope you could appreciate this. At least for me, it was an aha feeling. Oh, it's this way it works. I got it from, I would say, from one specific book here. So let's go back and go through this in detail. First, the dynamic programming part, and now we have expectations. The expectation operator, because now we are looking at the probabilistic setting. So what we are going for is a specific state S0, where we have the expectation of the sum from k equal 0 to infinity of the immediate rewards from one state to another state, and with a specific action. And this, once again, gamma function, the discount factor. And the discount factor, as I said, could be, say, from 0.9 to 0.99 typically. Bellman's equation for an arbitrary state, now I formulate that directly as this one. And if you compare with my solution before, first I changed from J to V, And that was because of my co-author. He proposed that we should use the notion V instead. And yes, I have to agree that in most literature, I would say it's maybe more used V, but J is also quite common as a notion for the reward function. So if you remember what I showed you before, Bellman's equation in that case was for p equal 1. So it was the sum of the reward plus gamma, and then it was J star and the next state. And now we have also introduced this probability function, which generates a distribution of how much we should count the different states, their reward and their next state loss function or reward function, total reward, sorry. Now we also introduced then here the Q function for this sum, and that means that we can reformulate Bellman's equation in this way, and you see that the derivation here is not detailed. So here we have the Bellman equation in the Q version, so to say. And the difference, once again, compared to what we had before, is now that we have this probability P. But as before, we have an optimal control policy. I call it mu, here it's called pi. And that is the argument that maximizes the Q function. Q learning for deterministic systems is like this, and the model-free function looks like this. And then it's interesting that if you take this deterministic version, it's definitely different to the stochastic or the probabilistic one, because the P function has now disappeared. But when you go for, so to say, the online or the model-free Q function estimate, you will get exactly the same result as in the deterministic case as we have already derived. So just to once again repeat, this is the Q function in its probabilistic setting. Now we have here an average of the random variable, this one. This is considered now as a random variable. And we have a probabilistic setting here. How should we be able to get an average estimate of this? Well, the average estimate is, as always, the sum of the elements of the samples we have and divided by the number of elements. Now, if we formulate this as a recursive function, we can first see that, okay, k plus, if we look for m hat of k plus 1 is 1 over k plus 1, and the sum from 1 to k plus 1. But then we can move up this k plus 1 to the left side here and get k plus 1 m hat k plus 1 is, and then what is written on the other side here is actually, you could say, the last element in this sum is then xk plus 1, and the rest in this sum is actually k m hat k. So this is altogether this sum when we have sum up from a equal 1 to k plus 1. But that can be described as k m hat k plus xk plus 1. And then I just take the element m hat k minus the same. based on this, I mean, this was just trying to make a recursive formulation of this very, very well-known average calculation. Then we see here that if you put the learning procedure here equal 1, then you have okay, sorry. If you divide then with k plus 1, then you get here you have x of k plus 1 minus m hat, and here you have k m hat k plus m hat k, and they two together generate k plus 1 m hat k. And then if you divide with k plus 1, it means that you only get m hat k here, and on the right side, sorry, on the left side, you get also m hat k plus 1. So it's actually here 1 over k plus 1, which is this gain factor here, or learning factor, and the elements that are left here are xk plus 1 minus m hat k. This formula is actually called Robbins-Monroe Stochastic Approximation algorithm from 1952. So, and this is a so big issue in the probability theory. And look, it's this extremely simple derivation. So I was a bit surprised when I read, this is really a big thing in the probability theory, and it's not more than this, because people always refer to this Robbins-Monroe stochastic approximation. So stochastic approximation is just this. And now we apply this extremely general equation on this formula. And then we take x hat k plus 1 of is s comma a equal x hat k. It's just that we replace m with q, nothing more, and its arguments. And then you have alpha k plus 1. And then we note that this is the stochastic variable, is the random variable, where we now replace rho with r prime. And here we have already the next state. So it's not a big thing. So what we see here is actually xk plus 1 is this with rho replaced by r prime. It's the actual value of this function minus the current estimate. And you could say that what we are doing here also is that we take the estimate here, which is maybe not absolutely, here we make an approximation in the fact that, okay, we take an observation of this random variable, but we have to take that observation knowing based on what we know, namely only the q hats. So I mean, it sounds reasonable, but it's for the next step. Okay, so by this now we can actually move this minus q hat out from this sum, and then we get 1 minus alpha multiplied by q hat plus r prime plus gamma maximum of q hat for the next state. And I haven't written that because you could say that, well, okay, This is still the Q function, update, the Q learning, but you can formulate it in a way which was more related to what I showed you before. And it's interesting that it's exactly the same equation that I formulated in a deterministic setting. And now we have made a complete stochastic setting and we get the same result. At least in my view, quite interesting. For deterministic system, the optimal learning rate is alpha equal 1. So that means that we go fully for what we have here. But since we have, so to say, also stochasticity, we also need to trust a little bit on the former estimate. Q hat converts to the optimal Q function if the learning rate satisfies the following properties. That the sum is from Q equals 0 to infinity of the square is less than infinity. It's finite, while the sum of the non-square, the alpha k itself, goes to infinity. And since alpha k is less than 1, it's clear that the square of alpha k will go faster to 0. So it's reasonable that that could be finite, while the sum of alpha k itself could be infinite. And it's actually the 1 over k of alpha k satisfies this, but what people have realized in practice is that, and this is especially in Gusavi's book on reinforcement learning, suggests that alpha k should be equal either log k divided by k, means that it goes not so quickly towards 0, or say alpha k equal 150 divided by 300 plus k. It still means that alpha k goes to 0, but not so fast. Okay, so this was a little bit more details around the derivation of the reinforcement learning. And now it's interesting to see what happens if we also include this automata related to this. So here I have the MDP, and now I introduce a specification saying what? Well, I argue that R is a forbidden state. So I should definitely avoid state 2 and state 10. And on the other hand, I would like to obtain a function which repeatedly arrives into state P, or state 0 with state label P, but also state 9 with state label Q, which means that it's not okay to move around like this, because then I will not satisfy that specification. And it's also not okay to go around here to get this state Q repeatedly, but not P. So both of them I would like to have. And then we could expect that, well, a native solution to this is that we go this way around. And you see here that it's actually critical that we never take the decision B here. We must take an A, because if we take B, there is an immediate risk that we get into that forbidden state. And here, when we are in state 3, we must definitely avoid action C, because then, although it takes some time, we will reach the state 10, where we have the forbidden state. Well, the Q-learning with the product and so on. Okay, we can say here that the automaton for this description is a bit more complicated, and I will not explain the details around that. Just telling that, okay, it's possible for any temporal logic expression to replace it with a Biki automaton, and then you take the product of the Biki automaton and the original system MDP. And then the idea is that, okay, you could have from the beginning some rewards. In this case, actually, we don't have an explicit rewards from the beginning here, although I had that in the first example here. Here I had a reward, say, with a priority for event B in state 2. So that's also possible with my formulation here. But for the marked states, I put a positive reward. And for the forbidden state, definitely a negative reward. So that means that for this state, I put a quite high negative reward. But I also need to add some positive reward on state 9 and 0. But if I only do that, it's actually not so easy for the reinforcement learning to reach a good solution. This Biki automaton helps the convergence of my solution, and that is the motivation. That's one motivation to introduce this temporal logic expression. And this has been quite popular only the very recent years. I saw the first papers. I had the idea myself 2018, and then I hadn't looked at the complete literature, and then a year later I realized, oh, okay, quite a number of papers have published something on this. So once again, I wasn't first, as quite often. But I mean, it's definitely very popular. And then I've had some local master thesis work and also this work. And I see that there are popping up a number of new publications on this. And the most recent was from UCLA, University of California in Los Angeles, where they made something more or less the same as we have done here and what I did with my PhD, my master student. Unfortunately, we didn't publish his results. I say this just to tell you that this is hot stuff. Okay, with the safety and liveness restrictions, we see that this is actually the solution that will come up as the optimal solution. And with what is interesting here is that now I introduce a regular language safety specification instead of an LTL expression. So I just say that I would like to have P and Q repeated. That means that, okay, I should not only go for this, I should also go in this direction. And this can also be expressed with this formulation. And now I don't tell that this is a Biki automaton anymore, but those are small details. And this is just to inform you that, okay, I can also introduce other types of specification, and I can also introduce supervisory control aspects of this. And now it's interesting to also look at local safety analysis. This is quite interesting. That if you have some partial knowledge, then you could, for instance, say that, okay, I know that I have a transition to this, and then you could stop this. And I also can realize that, okay, this is a forbidden state. So to avoid that state is also a good choice. This means that I have some knowledge about the behavior, but I would like the system to learn the best optimal behavior, the reinforcement learning to learn the best behavior. Okay, so this last comment here is that, okay, there are some way to improve the Q learning by additional system information. And I think I will only emphasize on this fact that, which I did here before, that, okay, if I add some temporal logic expressions, it can definitely help to guide the search in the reinforcement learning. Because let's say here, if you put a reward on this function, on this state, okay, it's not a big problem for this application, but assume that this state is quite far away. Then you will never experience any reward before you have reached that state for the first time. And it could take very long time before you reach a state for the first time if you don't have any guidance on where you have your sort of say reward states. And there are a couple of different guidance routine, and we believe that this temporal logic is definitely an interesting feature there. Okay, so based on that, you could say that reinforcement learning with its formulation down here is now a very, very popular procedure, and you have some tuning parameters here, the learning rate, the gamma value, but not very much more. Yeah, it's this epsilon greedy part. How much should you skip this maximization and instead just take an arbitrary choice of actions instead of something that maximizes this? This is also a lot of a number of different alternative solutions to this epsilon greedy. Well, based on this, I ask if you have any questions, because otherwise I think, yeah, okay, in any case, it's time to leave this now. And for this evening session, I will show you some MATLAB functions, and I will also discuss a little bit on how to make reduction of system based on different abstraction principles.
Thank you, Professor. Questions, participants? Today, all of you are so quiet.
So maybe this is completely new for most of you, or? Yeah, okay. No.
Like many of them.
Yeah.
So if there are no questions, my request to all of you is to please put on your videos so that we can see you, that you're there, and also to take your pics. Shubhangi, your
okay,
usual
so
role.
then I leave you and thank you, and see you in the afternoon.
We need a second of yours to get a click by Shubhangi. Thank you. Shubhangi, you've taken?
Yes, ma'am, I've taken.
Okay, thank you, Professor. Thank you so very much.
Thank
we
you.
are meeting at
Bye-bye.
6.
Yeah.
6 p.m. Sorry, Yeah, 6 p.m. IST. Yeah.
Yeah. Thank you. Bye.
Bye. So participants will be meeting after a short while. And I request you all to please be present before time. And please, my request is if you can ask questions, that would be great. This was a very interesting topic on reinforcement.